Hello, I'd like to thank the organizers for inviting me. It is unfortunate that I was unable to be present physically. My previous 2 visits to Canada were quite productive, but okay, in any case. Part of this talk describes some joint work with Luis Velázquez and with Luis Pereira, which is a student of mine at Porto Alegre. So our motivation, we're motivated by certain elements from classical Markov chains and the classical problem of calculating mean heating times. So our questions are very elementary in a sense. So we started thinking about this problem a few years back, and we have obtained, as time passed, some small collection of interesting results, and it's been quite fun to explore and try to find something we would call quantum analogs of certain notions or certain quantum versions of classical results. So our motivation is something that in the classical literature we call the mean heating time formula. Let's discuss this. Given a graph and some transition probabilities between its vertices, what is the mean time for a walker to reach vertex J for the first time, given that it has started at vertex I? So we call Tj the time of first visit to vertex J. Pi of Tj equals T, the probability that Tj equals T starting at I. So this is the formal definition of mean heating time. So what we're looking for alternative ways of calculating this mean heating time. So in the classical theory, if you have an irreducible finite Markov chain, you have this quite interesting formula. And in terms of this matrix Z, so P is the stochastic matrix associated with the chain. Omega is the stochastic matrix whose columns are given by pi, which is the unique stationary distribution of the walk. So this is something Aldous and Phil call the mean heating time formula. And Z is something they call the fundamental matrix. So a small comment we can make right here is that this matrix C is a generalized inverse of I minus P. And this is something we're going to discuss and explore a little bit more later. Okay, so our basic question, are there quantum versions of this formula? Motivation, they are first of theoretical interest, so we're not claiming that to obtain mean heating times in terms of the fundamental matrix is easier than by performing a direct calculation via definition. So in both cases, you have to go through the practical problem of calculating matrix inverses. Brief outline of this talk. So we're going to present a mean heating time formula for positive, irreducible, trace-preserving maps. So this is one generalization of the classical formula. Then we're going to discuss another formula, which is inspired by Kameni's, Nell, Meyer, Hunter, which are classical authors from the theory of Markov chains. And later, we're going to discuss what can we do in the case of reducible positive trace-preserving maps. So this is especially interesting because this is the case where you are able to talk about unitary walks and unitary conjugation. So we would like to go a little bit further the irreducible case so that the unitary case can be considered as well. So we're going to adopt here something we call the monitoring approach, in which a measurement of the walk is performed after each evolution step to check whether the system has reached a state lying in a prescribed target subspace V or not. So for this purpose, we need to associate to this subspace V certain orthogonal projections, conditioning on the events the system is in a state lying in V, or not. So let's take V, a subspace of the pure state Hilbert space Hn, where the operators, they are represented by the matrices of Mn. So if P is the orthogonal projection onto V, Q the complement, we introduce the orthogonal projections, which are essentially the conjugations on the left and on the right of P and Q, where the mixed states live. So we have P plus Q plus R equals the identity. So R is the orthogonal projection onto traceless matrices. So given a pure state, we are able to define the probabilistic notions of interest to us here. So we call PR of phi to V the probability of reaching subspace V in R steps when starting at phi. Pi R of phi to V is the probability of reaching the subspace V for the first time in R steps when starting at phi. We call pi of phi to V the probability of ever reaching the subspace V when starting at phi. This is what we call the hitting probability. And finally, the notion of interest in this talk, we call tau of phi to V, the expected time of first visit to subspace V when starting at phi. And this quantity is the mean hitting time. So phi is the initial state, V is the arrival subspace. So in the case that subspace V is one-dimensional, so this is something we can choose another notation, so we can simplify. We can write pi of phi to psi, and so on. Okay, so if anyone has any questions, please feel free to interrupt. Okay. According to this monitoring approach, we can express these notions in terms of trace calculations acting on the density matrix of the initial state. So PR of phi to V can be written in this fashion. So it's the trace of reaching the goal subspace of interest after R steps. If we are trying to determine the time of first visit, we alternate the evolution phi with proper projections onto the complement. So you evolve one more step and then you check whether the first time of visit is time R, and so on and so forth. So the probability, the hitting probability is a summation of those PRs, as these are disjoint events, and the mean hitting time can be written accordingly to this expression. So, and of course, we are interested in the cases for which the hitting probability equals 1. Otherwise, this mean hitting time equals infinite. Okay. In order to work with such quantities, we define this generating function. So this object is analytical because with respect to operator norm, the norm of Q equals 1. While the Russell-Dye theorem implies that the norm of phi equals 1, since we are assuming this positive map phi is trace preserving. So this generating function is interesting because as you make Z approach 1, we are able to calculate hitting probabilities and mean hitting times. So we define these two operators, H and K, as X approaches 1. So, and the reason those limits exist, so is that, well, first, as limit of positive maps, H and K are positive. So this is the hitting probability map and the mean hitting time map for V. And so since we are assuming phi is irreducible, so we have a finite dimensional space. So we know that 1 does not lie in the spectrum of Q phi. And so we are able to ensure the analyticity of G at Z equals 1. So this allows us to replace Z for 1. So we have these two very useful expressions for H and for K. So this assumption that one does not lie in the spectrum of Q phi is of great importance in several occasions in the study of this theory. So for now, if you have an irreducible map, you have this condition, so you are able to write these expressions, for instance. One last ingredient is to consider something we call a V-dependent block matrix representation of a linear map. So if you have this map T, so you have to write this block matrix. T11 corresponds to project to the left and to the right with I minus Q. T12 this object, T21 this one, so on and so forth. So this block matrix representation is the object that allows us to try some kind of analogy between the classical proof of the mean heating time formula and an operator version of that result. So this is one of the objects we need to deal with. So in terms of this block matrix representation, you are able to write heating probabilities and mean heating times in terms of the appropriate traces. So H and K are those block matrices. We're going to see an example a little bit later. So with this in mind, we can go back to our question, which is, are there quantum versions of such formula? So we can answer yes. So in order to do this, we realize that a natural generalization of the fundamental matrix for a positive, irreducible, trace-preserving map on the complex matrices can be given by this expression. So I is the identity map on the matrices, pi is the unique invariant state of phi, and so the identity is a fixed point for the dual of the operator, which comes from the trace preserving condition. And so with all these ingredients, we are able to state this result, which is something we call a mean heating time formula for positive maps and orthogonal states. So if you have Z, this associated fundamental map, K, the mean heating time map, and D, its diagonal part, you have the mean heating time to reach subspace V starting from phi is given by this trace expression. And so this happens for every choice of psi in this goal subspace. So you have this peculiar characteristic that this quantity trace of DZ11 is independent of the choice of psi. This is very easy to verify in examples, and this is quite evident from the proof. I don't have time to go through all the details of the proof, but some of the elements we have discussed just now. In word, the meaning of this formula is the mean time of first visit to a subspace is an information which can be obtained essentially in terms of the fundamental map of the dynamics and the mean return time map for such subspace. So we have a version for positive maps and non-orthogonal states. So under the conditions of the previous theorem, you have that the mean heating time equals 1 if you have already started at the goal subspace. Otherwise, the mean heating time is 1 plus this expression, which corresponds to avoiding the goal subspace in the first step and then trying once again to reach it. And then this guy, after the first step, is a state in the complement after normalization. So you can essentially employ the first formula to obtain your result. So one more comment. One of the main steps of the proof of these two theorems is to realize how to obtain a quantum version of something we call in the classical theory and conditioning on the first step. This means how to obtain a generalization of this classical expression, which is the mean time to reach J is the same as to calculate 1 plus the weighted average of avoiding J at the first step and then calculating these other mean heating times. So, and it turns out that we have a really nice generalization for positive maps for this expression. So you have that the mean heating time from phi to the goal subspace is 1 plus an expression which takes in consideration that you have avoided the goal subspace in the first. So far, we have a mean heating time formula for the case of irreducible, trace-preserving positive maps on finite-dimensional Hilbert spaces. So we are interested now in the following question. What about positive maps that are reducible? So typical examples are conjugations, so where U is unitary. So we would like to say something in terms of, we'd like to find some heating time formula for these cases. So first we have to think about it, and does this question even make sense? So we have one idea. So the idea is, first, we can consider a randomized map of the form this one. So you have a convex combination of phi, which is an irreducible positive map, with this unitary conjugation U. So you can show that lambda will be also irreducible if you are assuming that phi is irreducible. This is a really nice result which follows by an article by Daniel Burghardt and his colleagues. And so actually his proof regards ergodic channels, but the generalization for irreducible channels is quite straightforward. So with this randomization in mind, we can ask what happens as P approaches 0. Can we obtain a mean heating time information on this unitary map? Meaning that for the irreducible case, I have a mean heating time formula in terms of this fundamental matrix. But we have a problem, which is the following. The matrix representation of U is the tensor product of U with its conjugate matrix. So what happens is that 1 is a degenerate eigenvalue. So the fundamental matrix Z, which relies on the existence of a unique fixed point, is not even well defined in this case. So the problem is, so you can't just take P to 0 and expect that everything works just fine, or does it? What happens is that we are able to find examples such that if P approaches 0, the expression regarding the trace of K11 and those block entries associated with the fundamental matrix, in fact, produces the correct value of the mean heating time for the unitary map. Of course, assuming that the heating probability equals 1. So the trace calculation in terms of Z converges to a finite value as P approaches 0, although Z itself does not exist for the unitary case. So, but perhaps, and here is another idea, some other generalized inverse of I minus U exists, and perhaps this might be applied to the calculation of heating times. So this comment is motivated by the fact that for P stochastic and irreducible, Z is a generalized inverse of I minus P. So, well, then another question. In the classical case, are there heating time formula in terms of generalized inverses that are different from Z? So we have replaced one question with another. Well, quick question, yes, but let us briefly review this. So a generalized inverse, or a G inverse, as we're going to call it here, of a matrix is any matrix A minus such that this expression is satisfied. So usually one can obtain several generalized inverses, but by imposing additional conditions, one may or may not have uniqueness. So we have this proposition by Jeffrey Hunter from this really nice article. If you have an irreducible Markov chain on a finite graph, you take E to be this vector with all entries equal to 1, Tu complex vectors such that these two inner product conditions are satisfied. You learn that I minus T by this matrix is invertible, and its inverse is a G inverse of I minus T. After that, Hunter shows that any G inverse of I minus T can be written in this really interesting form, which regards the inverse of this expression plus these two matrices, where F and G are any vectors. So this is a quite interesting result. And well, after that, one of the results he proves in this work is this more or less well-known formula regarding mean heating times. If M denotes the mean heating time matrix, D the diagonal matrix whose entries are the ones given by M, and E the matrix whose entries are all equal to 1. If you take a G inverse of this form, then you can write the mean heating time matrix as this very interesting product of D and the generalized the G inverse and the diagonal of the G inverse. So the proof is quite elementary, and Hunter is not the only author to have come up with this expression. Actually, Snell has a work with this expression as well. Kallmeyer also has another derivation of this expression. From this, we can ask, is there an analogous result for quantum or positive maps in terms of something we call quantum Markov chains? So, and now the unavoidable question is, what are quantum Markov chains? So let us briefly review this. Okay, we're gonna take this collection, this special collection of density matrices. This is actually a direct sum of positive semi-definite matrices whose traces add up to 1. So this is a collection, specific collection of density matrices. And we're going to say that N, which appears here, is the number of vertices of some chosen graph, and K, which are the sizes of those matrices, is something we call the internal degree of freedom. And we define this operator T acting on a density matrix of this form. This is defined by this block matrix product, where each one of those phi ij is a positive map, so that we have this trace preservation condition with respect to columns. So this block matrix computation is what we call a quantum Markov chain on n vertices and an internal degree of freedom k. A simple picture to illustrate this. O, I, J, K, L are the vertices. So you have a walk realized on those graphs. And each one of the phi ij is a positive map describing a transformation in the internal degrees of freedom of the particle during the transition from vertex J to vertex I. So those graphs can be either finite or infinite. In this work, we're going to focus on finite graphs. And in the case that each phi ij is completely positive, those quantum Markov chains, or QMCs, as we're going to call it, these were defined by Stanley Goddard. And in the case that phi ij are simply conjugations like this, a particular case of completely positive map, we have something we call open quantum random walks, as defined by Stefan Natal and his colleagues. So this is a formalism for studying certain kinds of quantum dynamics on graphs. And inspired with this formalism of QMCs in mind, and inspired by a result which comes from Kameny, Snell, Meyer, Hunter, we were able to prove something which is something we call Hunter's formula for QMCs. So we're going to take an irreducible QMC on a finite graph, pi its stationary density, and omega its limit map. Using the previous notation, K is the matrix of mean heating time operators to vertices I from 1 to n, D the diagonal block matrix, and E the block matrix for which each block is the identity of other K squared. So if we take a generalized inverse of this form with any kind of arbitrary f and U such that this inner product condition is satisfied, you have this heating time formula in terms of any generalized inverse of this form. So once again, informally, the meaning of this theorem goes in complete analogy with the first heating time formula we saw before. The mean time of first visit from J to I is an information which can be extracted from the mean return time to vertices, which is an information codified in matrix D, and any generalized inverse of I minus T. We're going to briefly illustrate this later with an example. Let us discuss our conclusions so far. First, we have a mean heating time formula for any irreducible trace-preserving positive map. So we are always able to talk about the fundamental matrix Z in this case, since the fixed state is always unique. Later, we have another mean heating time formula, but this time for any irreducible QMC, a quantum Markov chain. The interesting point here is that you are able to consider other generalized inverses other than Z. And so the latter allows us to calculate heating times in terms of any G inverse. And so with those conclusions in mind, we can go back to our question. What about a mean heating time formula for positive maps that are reducible? So we are insisting on this point since the reducible case is more or less well understood. We're going to insist on this question. What about the reducible case? Well, here's what we can do. We noted previously that one can obtain heating times of randomizations of positive maps and then take the limit p to 0. Well, this holds for unitary conjugations and other reducible maps, but we saw that the problem is that in general the fundamental matrix doesn't exist for such examples. Later, we have obtained another formula following Hunter, so any generalized inverse can be chosen, and heating times for irreducible QMCs can be calculated. So you can perform a randomization procedure in this setting as well, and so you can obtain similar results. Well, QMCs are a particular case of positive maps, but of course not every positive map is a QMC. So with all this in mind, we can ask another question, which is there a Hunter formula for positive maps that are not QMCs? So up to our knowledge, such a formula has not been established so far. Nevertheless, given a positive map, we can consider the QMC induced by such map and then apply Hunter's formula. So the natural question is, what is the QMC induced by a positive map? So the idea behind this has already appeared in previous slides. So which is the following. If you take any vector subspace V, we recall that we have considered this block matrix representation. We have written in this way, which is a slightly different way of writing the previous block matrix representation. So by looking at this representation this way, you define this operator TQ So B of V corresponds to the linear bounded operators acting on the subspace V. So you have this direct summation. And this object you simply call the map induced by T with respect to V. So this is essentially the same idea discussed previously for the first mean hidden time formula in terms of Z. So, and one small comment, the idea of employing block matrices of operators in this form, in the context of first visit return to subspaces, this has been illustrated, for instance, in a work due to Alberto Grunbaum and Luis Velázquez. So this is partially a motivation for employing this formalism. Okay. So this induced QMC essentially is a way of associating to any positive map a two-vertex graph on which you have these four operators associated with reaching a subspace of interest or avoiding it altogether. So this is a schematic illustration of this QMC induced by T. So this is a way of associating a positive map with a graph. Okay, it is a graph with two vertices, but this is enough for our purposes of calculating hidden times. Okay. So it is a simple matter to explain that as we replace a positive map by its induced QMC, we do not lose the information we are looking for. In particular, the induced map is in fact a QMC. If T is irreducible, the induced map is irreducible. Hidden times calculations for the induced QMC produce the same values as for the computations in terms of T. So what we have so far. So let's take phi any positive trace preserving map. If phi is irreducible, then since Z exists, apply the first mean hidden time formula and we are done. On the other hand, if phi is reducible, consider a randomization and take P to 0, then hidden times are obtained as well. Question, what about explicit expressions for the G inverses in the reducible case? So we have already seen that Z doesn't seem to have an obvious version for reducible maps. And moreover, there are several G inverses for irreducible maps as observed by Hunter. But then once again, what about reducible maps? So in other words, what we are trying to say, the hidden time expression and this kernel exist and are finite, both in the irreducible and reducible cases. Well, in the latter, you have to assume that the hidden probability of reaching subspace V equals 1, of course. And regarding randomizations, G inverses always exist if P is greater than 0, but in the limit, this usually fails to produce an explicit G inverse for the reducible case. So what are we looking for? What we would like to find is a G inverse that could be obtained regardless of randomizations and such that its existence is guaranteed even in the reducible case. So is there such a G inverse? So quick question, yes. And so how does this work? So one quick comment. So up to our knowledge, there are no results on reducible positive maps for which hidden times are discussed in terms of generalized inverses. So in particular, given a quantum walk, a unitary quantum walk, given in terms of a conjugation, we did not find in the literature a discussion on statistics of the walk in terms of G inverses of I minus U. So perhaps this is due to the practical problem of calculating G inverses. So with this in mind, let us discuss one particular inverse we believe is of interest to this and other matters. So this is not something especially new, but this is something we believe it is worth taking a good look. So a small piece of linear algebra. So if you take a complex order n matrix A, so there is a non-integer k such that Cn can be written as the sum of the range of A to the k and the kernel of A to the k. This smallest such interest is called the index of A. We write it like this. And this is equivalent to say that the index is the smallest integer such that the range of A to the k equals range of A to the k plus 1. So with this in mind, we know that a G inverse satisfies this unique, this basic expression. If, moreover, we require that A minus satisfies these other two algebraic expressions, we will obtain something we call the group inverse, and we write it like this. And it is well known that the group inverse exists if and only if the index of matrix A is less or equal to 1. So, and when it exists, it is unique. There are a few methods for explicit calculations of the group inverse. For instance, you can perform this limit. So this is a theorem. You can see it in an article by Meyer. So we have a practical procedure of using a computer and calculating those group inverses. So this is not very difficult in general, at least for small examples. And with this in mind, the basic result we need is the following. If phi is a positive trace-preserving map, the group inverse of I minus phi always exists. And this follows from the basic fact that for every positive trace-preserving map, all Jordan blocks of unit modulus eigenvalues are one-dimensional. In particular, we are able to calculate I minus U explicitly and explore them in examples. So here's one example. So you take these four matrices acting, so you're able to define this quantum channel phi, which is the polarizing channel on one qubit. You can take U to be this unitary matrix and this randomization channel. So this is a unital irreducible channel. And we can take a phi, a start initial state, psi, a goal state. You can define the proper projections as before, and you can make the usual calculation, mean hitting time of reaching phi if you begin at phi. You have this expression, this is the value, so just recall that S is the parameter of the polarizing channel, and P is the parameter of the randomization. And as P approaches 0, this is consistent with the direct calculation on U, for which you can just calculate this trace in terms of U directly instead of the randomization. So you can find the answer is 4. So noting that you can use this formula because 1 is not in the spectrum of key U. Okay. Well, now I can take the QMC induced by this randomization. So we are going to call GG the group inverse associated with I minus lambda P. So this depends on P, okay? You can calculate Hunter's kernel explicitly as a function of P, and as expected, the mean hitting time is verified. So moreover, you can note that GG depends on P, and that although the limit of Hunter's kernel exists as P approaches 0, we have that the limit of GG itself as P approaches 0 doesn't. So what happens here is that the group inverse for U cannot be obtained explicitly by taking this limit. The group inverse always exists. So there has to be a way of obtaining explicitly this guy. So, and in fact, if you perform one of the procedures of making an explicit calculation of the group inverse, if A equals I minus U, here it is, the group inverse. So satisfies these three equations. So this has to be the group inverse, the unique group inverse. So this can be calculated with the limit theorem stated before, or via an algorithm involving the characteristic polynomial of A. But this is explained in detail. So this above expression for GG, which is the group inverse, refers to the G inverse of the QMC induced by I minus U. So as U has order 4, the induced map has order 8. So that's why this matrix has order 8. So what happens here is that Hunter's formula holds as expected. So you can take this trace. The answer is 4. And now we have, unlike our previous attempt, an explicit expression for the group inverse of I minus U as well. So, so the last thing that needs to be said is how to prove a mean hidden time formula for positive trace preserving maps, which includes the reducible case. So as we want to include a reducible case, you cannot suppose uniqueness of a fixed point, as it is the case for Hunter's proof. And so a natural question is, what about a variation of Meyer's proof? So these two proofs of these hidden time formulas are quite different. And so regarding Meyer's proof, it turns out that with this collaboration with Luis and motivated by our previous results, we have a positive result regarding that. In fact, we have a nice conclusion, which is if you have a positive trace preserving map V a non-trivial subspace so that 1 is not in the spectrum of Q phi, you have that Hunter's formula holds. So essentially, you are replacing the quite strong assumption of irreducibility by the importantly weaker assumption that 1 is not in the spectrum of Q phi, so that you are able to write this hidden time formula. So you have for the unitary case a hidden time expression in terms of a G inverse, which is in this case the group inverse. Okay, so just to finish, two basic references for the classical mean hidden time formula are these two works. The first one is very, very classical work, is the unfinished monograph by Aldous and Phil. You can download it for free on their webpage. Pierre Bremot have a really nice book with a really nice algebraic proof of the hidden time formula. Aldous and Phil's proof is quite probabilistic. So you have two approaches to this formula. And other classical references, well, first is Meyer's article, which has this really nice discussion on the role of the group generalized inverse in the theory of finite Markov chains. The second one is Jeffrey Hunter's excellent article with all the details you need in order to understand this classical piece of mathematics. The third article I mentioned before is Burghardt's article on the randomizations and how ergodicity and irreducibility is preserved by randomization. This article has lots and lots of results. This is just one of several interesting results you can find there. And the fourth article regards one of the works that motivated our use of block matrix representation. So, these articles, the first three ones, regard some recent work on those matters of hidden time formula in quantum settings or in the settings of positive maps, if you like. And the last one is a preprint, which is almost ready. We are hoping to have it sent to archive and submit it soon. So, okay, I'll stop here. Thank you.
Hello. Luis, can I ask a question? Hello.
We can hear you.
This is Alberto Brumbaum. Can I ask a question?
Yeah, you can ask.
Yes.
Question.
Okay,
yes,
first, nice to see you guys. Just this is totally out of the blue. I'm sure it has no interest whatsoever, but I'll ask anyway. You define the index of some matrix A in terms of some dimensions, of the smallest integer or something or other should happen. And the question is there any chance, I mean, that looks like a very basic linear algebra question, definition that is, any chance of getting a topological meaning to that index? Could it be the winding number of something or other, some curve, or something much more complicated?
I don't know. I don't know. Good question. I think I'll ask Luis this question.
Very good.
I think he's better equipped to answer this.
By the way, in the definition of the index, I don't know if you can go back to that page.
Okay,
it's not too far from the end. We're getting close. We're getting close. Now, you wrote in there non-integer k. You really mean non-integer?
Wait. I think I meant there is a non-negative.
Oh, okay. Okay, fine.
Okay, I'm sorry about that.
No,
It's not a non-integer. It's a non-negative.
Everything is an integer here.
Sorry about that.
Okay. No, but this looks like such a nice and basic linear algebra thing that maybe somebody has found some different meaning for that. I mean, I'm sure you can write that in terms of the difference of the dimension of a kernel minus the dimension of a co-kernel and so on. The usual definition of index, or one of the usual definitions, but maybe there is a topological way of looking at that just for fun. Okay. Very nice talk. Very, very nice talk. Thank you.
Thank you. Thank you.
Renato had another question. Renato?
I think Renato wants to talk.
Carlos, do you know that paper by Szegedy on quantum walks?
Which one?
It's 2004.
The first one?
Yeah, it's an old one where he defines a quantum heating time there. So he defines a quantum walk, or the process is unitary. And then he defines a function that is a time average of the norm of the state of the walk at time t minus the initial state. So with that function, he is able to define a heating time, and it works fine. So I understand that your method is much more general, is very broad. So you are using quantum channel, very general quantum channel. So it goes much further than what he has done. But my question is whether Szegedy's definition is a special case of your method. Have you analyzed Szegedy's insight, your method?
If I well recall, I think the definition of heating time that Szegedy and other people like Childs and Bainis, they're essentially equivalent in the sense that as you have a step-by-step verification as to whether you have reached a vertex, you have some kind of projection onto the complement, and at some point you project on the vertex of interest, and then you calculate the probability of reaching, the probability of finding the particle on that particular vertex. So I think in terms of the definition of heating time that Szegedy and others employ, I think it is the same definition. The definition of heating time, I believe it's the same, but I'm not an expert expert neither on indices and neither on the literature to be completely sure that no one has ever talked about unitary walks in terms of G inverses. Perhaps this has appeared via some different path. I don't know.
Okay, thanks.
Luis, can I ask one thing to make sure that I understand both Renato's question and Carlos' answer? So what Carlos is saying is that in both cases, there is some kind of a monitoring approach being taken into account, right? With these orthogonal projections and so on, both in what Szegedy is doing and what you guys are doing, right?
Question for me or for Carlos?
Well, now that I'm thinking about this again, I recall reading Renato's book, I think, and there is a really nice chapter on heating times. And I think Renato is following some of the formalism that Szegedy does on his articles, but I'm not completely sure that the theory is discussed in terms of monitoring. I think this discussion of heating times is done in a slightly different way, and that's partially because if I'm not, correct me if I'm not wrong, Renato, I think the heating time discussion on your expositions regards continuous time unitary walks. Is that right?
No, it's discrete time. And in Zegedy's case, he does not perform a measurement after each step. The evolution is unitary all the time. And the only way to obtain the heating time is by defining that function that is a time average. So he used that time average of the norm of the difference between two vectors. And he also calculates the inverse of 1. But to calculate that, he has to go to a directed graph instead of using the original graph. By going to the directed graph, he defined a new transition matrix. So P changes, so is 1 over identity minus a new transition matrix, which is not, which has no problem, which has an inverse. So it is much simpler to what you've done. It seems to be a special case, but is simpler.
Well,
I'll think about it.
No, I was going to say, my suspicion is that if Szegedy is not using monitoring in any explicit way, I would bet a very small coin the results, the notions are different. I mean, what he's using and what Carlos and Luis are using here, unless by accident, they happen to be the same. Monitoring is here a very crucial thing.
We can talk some more about this, Renato.
Yeah,
we can talk some more about this later.
It seems that the organizers have set up a place for discussion. I recall receiving an email about that. Maybe we should go there and have a chat over there.
Thank you for speaking.
Thank you.